Hello everyone, my name is Brian McMahan, and today I'll be talking to you about analyzing speaker strategy in referential communication. Simply put, referential communication is about identifying objects in context. To accomplish that goal, speakers and listeners have to coordinate their efforts. And so for a collaborative dialogue system, it is important to coordinate in the right kinds of ways. For that purpose, our work focuses on a small piece of that coordination puzzle. Specifically, understanding how speakers assess that references are likely to be successful. And so to begin, let's look at a few ways that speakers could be assessing their utterances. Shown at the top of this slide is a set of 3 color patches. A speaker was charged with referring to X0 so that a listener could correctly identify it. 2 possible choices that this speaker could have had are blue and royal blue. We treat speaker choices in a decision theoretic way so that the expected utility of these utterances matters. You can think of expected utility as a matter of costs and risks. Cost is related to how frequent words are. More frequent words have lower costs. Risks, on the other hand, is based on whether the speaker's strategy assesses that the utterance will succeed. Speakers could be using different strategies, but the speaker strategy being considered here assesses that blue is more risky because it could have been confused with the other 2 color patches. With the trade-off between cost and risk, speakers can opt to choose the higher cost utterance, royal blue. And in fact, a human speaker did choose royal blue to describe X0. Now, this is only one speaker strategy's view of risk. Risk is a matter of perspective. In this example, when presented with the color patches shown here, a speaker chose to say blue. Now you might think that blue wouldn't work because it simply doesn't identify X0 uniquely. But if a speaker expects the listener to meet them halfway, blue seems less risky. We call this a pragmatic approach because it requires the listener's cooperation. The listener has to conclude that if the speaker meant X1 or X2, they would have said something else. Alternatively, a speaker might assess risk based on the meanings of words. Specifically, a speaker might adapt their meanings to the context. In this example, the speaker refers to X0 as yellow, even though X0 is a borderline case of yellow. It isn't likely that it'd still be called yellow in all contexts, such as when a more prototypical yellow is present. Therefore, we can say that the speaker has adapted the meaning of yellow to this context. If the speaker thinks the adapted meaning will be accepted, then yellow seems less risky. We call this a semantic approach because it measures risk as the likelihood of the semantic interpretation. In this work, our approach is to look at the kinds of risks speakers take and draw inferences about how people expect to collaborate on a reference. For the remainder of this talk, I will begin by outlining how we modeled speaker strategies from a shared base model to a cooperative reasoning model, which requires the listener's cooperation, and a linguistic reasoning model, which relies upon the meanings of words. Then I will discuss how we use the speaker strategy models with a colors of context dataset. Finally, I will conclude with some implications of this work. In this work, the differences in speaker strategy are algorithmic. They all use the same model, pre-trained on the XKCD dataset, a dataset of color patches in isolation. In brief, the XKCD model computes a probability distribution over color descriptions when it is given a color value. It is implemented as a neural network that is extended from previous work. The code, pre-trained models, and data are all on GitHub, and you can see the paper for more details. The first speaker strategy model is cooperative reasoning, which is based on the rational speech X model of Monroe and Potts, but extended to handle a long tail of diverse vocabulary. An RSA speaker chooses descriptions by anticipating the listener's interpretations. Specifically, an utterance is probable if the listener can use it to identify the target. The second speaker strategy, linguistic reasoning, is a model we have named reference goal composition, or RGC for short, and in general generalizes previous work. An RGC speaker chooses descriptions based on their meaning. It adapts the meanings of each utterance to see if they can be used to refer to the target and not the alternatives. An utterance is then probable if the adapted meaning is probable. Once RGC has adapted its meanings, there's no further information it can gain from anticipating a listener who has done the same. So combining RGC and RSA results in the same probabilities you get with only RGC. Now this is just a high-level description. See the paper for more details. The final speaker strategy is a conservative baseline that embodies speakers who don't want to take risks. In this no-risk strategy, the probability of the base speaker and the base listener are combined. An utterance is probable if it fits the target, that is to say, if the base speaker would have said it, and if the listener can almost certainly use it to identify the target. Another way to think about the conservative baseline is that it weighs the base speaker's probabilities by the base listener's ability to identify the target. Equipped with these three speaker strategies, we can dig into the dataset and look at what kinds of risks speakers are taking. We use a dataset of 47,000 rounds of two-person reference games. All of the previous examples in this talk have come from this dataset. Each of the three color patch contexts in the dataset are categorized as one of the following three conditions based on the perceptual similarity of the patches. Far, where none of the patches are similar, split, where two of the patches are similar, and close, where all three of the patches are perceptually similar. For our experiments and analyses, we selected a subset of the rounds that only have one utterance, the speaker's utterance, and that utterance was a color description present in the XKCD lexicon. Our first analysis is twofold. First, it's a quantitative evaluation of how well each speaker strategy captures the uncertainty in what people say. Second, it's also a test of whether there's evidence for multiple speaker strategies in the dataset. To start, we collect the utterance probabilities for every data point under every speaker strategy model. The probabilities per model are used to compute the perplexity of the data under each model. Then the probabilities are used in a mixture model where we fit prior probabilities for each speaker strategy such that it maximizes the marginal probability of observed utterances. Finally, we compute the perplexity of the data under the mixture model using those marginal probabilities. The mixture model perplexity quantifies how well the combined speaker strategies capture the uncertainty in what people say in the dataset. The results are summarized in these two rows. The first row is the best independent model, which happened to be the conservative baseline, and the second row is the mixture model. As you can see, the mixture model has a lower perplexity score than the best independent model, which means that it captures the uncertainty in what people are saying in this dataset better. We take this to mean that in this dataset, there's evidence for different speakers using different strategies. All of the perplexity differences are significant under the Wilcoxon sign ranks test. Our second analysis takes a closer look at the data to ask the question, what kinds of risks are people taking? Are speakers taking? For the purposes of exposition, I will only show the analysis for the close condition, which was the most difficult of the three conditions. Our approach is once again to use the probabilities for the observed utterances, but this time partition the utterances based on which strategy had given it the highest probability. With those partitions, we then looked at task success, which is called metric success here. This approach will tell us what proportion of the data is potentially explained by which strategy, and we get a sense of how risky each strategy is. The results of the analysis are summarized in this graph. The first thing to notice is that there is a fair amount of data points in each speaker strategy's partition. Second, across each partition, the rates of success are significantly different. The data points in RSA's partition resulted in failure 1/3 of the time, while in contrast, the data points in the conservative baseline's partition result in failure only 3% of the time. Overall, this is evidence that different speakers are using different strategies with varying amounts of success. In fact, that is the take-home message of this talk. Each strategy is used in some cases by some speakers. If you want to take more home, there are some implications of our work. As well. First, each speaker strategy could be approaching the coordination dynamics of multi-turn conversations differently. It is possible that cooperative reasoning expects more from the listener, and so that in a multi-turn conversation, the listener has to not only meet the speaker halfway, but recall specifics about the speaker and their preferences. It's also possible that linguistic reasoning will rely on conceptual packs in a multi-turn conversation. So depending on the dominant speaker strategy, the relevant information to track over time will change. The second implication to take home is that these coordination concerns represent a challenge for collaborative dialogue systems. The system needs to match what people do both in anticipating speaker strategies and fulfilling the roles of each speaker strategy when it is its turn to be the speaker. And so with the methodology and observations presented in this work, we hope that collaborative dialogue systems will overcome these challenges and engage with people in a fully coordinated referential communication. Thank you for listening.